First, I would like to introduce our development members. Alex Valdivia, who's our project manager, Dennis Bustillo, and Noor, Al-Alami, and myself, Mariela, Vidal. We work on the response measurement system for sports training. First, I will begin by explaining to you what this presentation is going to cover. We're going to cover problem statement and design overview, followed by the approach and systems overview. We will briefly explain the sensors used and the functionality that I had to do into the circuit. And that will follow the microcontrollers. Microcontrollers was able to transmit the data obtained with the sensors wirelessly into the laptop and analyze there. And then we will end with some remarks. Problem statement. One of the major problems facing athletes today is risk of injury. This not only affects the player, but it also affects the team, and it can also affect the sports leagues. The market now doesn't have a system that enables coaches or training staff to identify players that are susceptible to injuries, but our system will measure muscle activity and force. How are we going to make this system? Well, we are going to use 3 sensors. One of them is the electrodes. This basically allows us to measure the muscle activity. The study of such signals is called electromyography, EMGs. Then accelerometers were also used. Both of these sensors were placed in the shin guard, and we also used the force sensor, which is placed at the sole of the shoe. The reason we chose this particular area here is because we wanted to focus our system to soccer. It was a group's decision, and also another thing is because it's a main sport that's played all over the world. Using these 3 sensors, we transmitted wirelessly into using the microcontrollers into a laptop, where we use MATLAB to analyze the signals and display the signals, so the coach could either choose breaks during training or substitutions. And how are we going to fit everything into something like this? Alex will go ahead and explain that part.
Thank you, Mariela. Evening, everyone. So we came up with that design concept. If you could gain valuable information from an athlete out on the field in real time, you might be able to effectively prevent injury. This could also happen during training or during rehabilitation. So the concept was to make everything happen in something like this. This is a standard soccer shin guard. I hope everyone can see it. Might protect any circuitry that's in there. But so how do we turn this concept into a reality? Where do we begin? Research, lots of it. We looked into sports injuries. We looked into electromyography, the measurement of muscle signals, EMG. And we also did a resurvey of commercial telemetry systems to see if there's anything out there that is already doing what we're trying to do. And it turns out that the closest thing is pretty bulky and doesn't really fit the bill as we determined the constraints that we wanted to follow. So then, after research, we did research design of the sensors, the data acquisition from the sensors, the wireless transmission of that data to a PC to display back to the user and also to analyze some of that data. That was the design approach, and testing along the way. And this is not a chronological list. These things happen cyclically throughout our project, not always in sync with each other. So it was kind of a constant cycle of all 3. So this is the system overview. On the top left, you'll see, actually on the left, up and down, you'll see the inputs of the system, the EMG signals, force, and acceleration. And we use the sensor modules. To measure EMG, we have electrodes, an amplifier stage, and a filtering stage. To measure force, we have a force sensor, an accelerometer for acceleration, and these are sent to the ABC to a microcontroller through an RF interface over radio frequency and to the computer for signal processing to display back in the user interface. And these all require so I'll talk a little bit about the force sensor that we're using. It's the FlexiForce A201. It's a capacitive pressure sensor technically, but since it can be hooked up to a circuit that's basically a force to voltage circuit, there's a linear relationship between force applied to the sensor and the resistivity in the circuit, so you can establish that linear relationship to measure force. Now Noor will talk about the electromyography system.
Before I get into the hardware, just a little bit of background information on what is electromyography. It's basically a measurement of electrical potentials of muscles. So basically every single time you contract your muscles and relax them, there's a potential difference there. Depending on the type of muscle you want to measure, the range can differ between 50 microvolts to 50 millivolts. Obviously, the larger the muscle is, the greater the voltage will be. And last, these EMG signals provide useful information on muscle response to fatigue and disorders. Now, this is our implemented circuit. In PSpice, we simulated an estimated voltage of 5 millivolts, and this feeds into an INA2128, which is a 16-pin instrumentation op-amp. Why we chose this op-amp is because it has a high common mode rejection ratio and high gain. So in our case, it was 120 decibels and a gain of 8. I'm sorry, that should be 99. This output feeds into a low-pass filter, approximately at 500 hertz, so that the sample EMG signal can get sampled at 100 samples per second to avoid aliasing. Later feeds into a high-pass filter with a cutoff at 15 hertz to eliminate any noise or motion artifact. And lastly, through an inverting amplifier to further amplify the EMG signal. Now this circuit was designed to have an output range between 0 to 3 volts, and to ensure there would be no crosstalk between signals. Now we wanted to ensure that our output of the signal works and makes sense. So what we did was a first simple test, just contracting your bicep muscle. So you have 2 electrodes on your bicep right here, 1 on your elbow for ground, and then this is our output right here. So you can see this is relaxed and it's contracted. We also want to compare our outputs with standard EMG devices. So this is the output of our circuit with the output of a sleep-loud fire radio.